Okay, so in this video, we'll take a look at the one of the other possibilities. It's essentially the same kind of combination circuit, but this time, instead of having a series portion with a parallel section, I'm going to put a series in the parallel portion. So in this circuit, we'll have one resistor in our first path, but in the second path, we'll have two resistors. Okay, we'll put the same two resistors. So let's do it this way. We'll say that this time R1 will be the 15 ohm resistor. R2 can be the 5 ohm resistor. And I'll put this one over here. R3 will be equal to the 10 ohm resistor. Okay, so again, we run into a problem where there's nothing in series out here with the battery, but in this branch, in this parallel branch, there are two resistors that are in series with each other. And what it means to be in series with each other is that the current that passed through here also passed through here. And I don't mean the same amount of current. I'm not saying that if 1 amp passed through here, then 1 amp would pass through here. I'm saying physically, the same charges that pass through this one will pass through here, all of them. There is no other place for them to go. So when that is true, that the exact same physical current is traveling through one resistor and then through another one, then they are said to be in series with each other. However, the current that's going through them is not exactly the same as the current going through here, because the current going through the battery also includes the current that went in the other path right here. So this is a portion of the current that went through the battery, but it's not all of the current. And so therefore we would not say that they are in series with each other. These two are in series with each other, but they are in parallel with the battery. Okay, so again, this same strategy is going to work. We're going to try to simplify this thing down, and our first simplification is to get to this circuit. So we want to eliminate the series part in here and get this down to one circuit, or one resistor. And the reason why we need to do that is because in order to use the rule for parallel, I need to know the total amount of resistance in this section. And right now it's broken up into two parts. So obviously that's a very easy calculation to make. That's just going to be 5 plus 10 to give me 15. So now I have two 15 ohm resistors. And then don't forget, we still have the, 12 volt battery. Okay, so I purposely set it up like this just so that you'll see kind of like an interesting thing. If you look at what we need to do now in order to get the equivalent resistance for this, so now we're going to try to make our last step. And that is to get to this circuit, in which we replace these two with a single resistor that will be the equivalent of that guy. So remember, that was 12 volts. All right, so when we do this calculation, 1 over Req is going to be equal to 1 over 15 plus 1 over 15. That obviously already has a common denominator, so no need to do anything there. Just going to add those two together to give me 2 over 15. So therefore, the equivalent resistance, this guy right here, is going to be equal to 15 over 2. Remember, you have to flip that over because that's the reciprocal of the answer, not the answer. And that would then be 7.5 ohms. Now, I'm not going to put a box around that, but I just want to remind you what we got for the equivalent resistance in the other circuits. Remember, the most resistance that we got was 30. That was with our series circuit. And then in the parallel circuit, we got the least resistance. That was only 2.73 as opposed to 7.5. So quite a difference with the parallel circuit. And then we did the other combo circuit, and we found that we had an equivalent resistance of 13.75. So that one actually produced a little bit more resistance than the circuit that we can see right now. Not surprising, because this has more of a parallel aspect to it, and the parallel circuits allow lots of current to flow through them always. Now, one of the things that I want to kind of point out about this is I intentionally made sure that these would come out to be the same. And the reason why I wanted to do that was to just get you to think about how you can calculate the resistance. This is very likely would show up on an IB exam or in an exam in my class, where you can follow the rule. Obviously, we can do this, and this will always work. But if you just realize that the rule in parallel, when you add identical resistors, means that you'll be putting 1 over that number, however many number of resistors you have. So let's say, for example, that I had 3 resistors there. Well, then I would have had 1 over 15 plus 1 over 15 plus 1 over 15 to give me 3 over 15, right? And why is it coming out to be 3? Because the 1 represents the calculation being made for each of these individual resistors. So the number of resistors is going to end up being the number here, and then when you flip it over, of course, you're going to divide by that number. So kind of a quick and easy rule is that if the resistors are all identical, and there's no series portion to it at all, it's just those resistors, then we can just simply divide the individual resistance by the number of resistors, and that would give us the total resistance of the circuit. So it's like a little trick that'll help you get through things a little bit more quickly. So obviously our next step then is to get the current that's coming from the battery. So that's going to be Vs over Req. That was 12 divided by 7.5. And that is 1.6 amps. Let's take a quick peek at what happened in our other circuits. Just to remind you, what were the currents when because these are the same resistors, of course, from our other circuits. We got a current of 0.40, so very small current, even smaller than this one. That was in the series circuit. In the parallel circuit, we were able to get 4.4 amps, so quite a bit more, nearly triple the amount of the current in this circuit. And the last combo circuit, where we had 13.75 ohms of resistance, we ended up with 0.873, so around half of the current that we got from this guy. So each of these resistors can produce lots of different currents and voltages depending on how we connect them together, even though it's just three simple circuits. Okay, so here at this point, I can actually tell you the voltage for V1 is equal to 12. And the reason why I can tell you that is because there are no branches once you get past this point in the circuit. So if I pass through the battery, I increase the voltage by 12 volts. As I move around the circuit and come down through this guy, I lower it by 12 volts. It must be like that because the next step is to go back to the battery. So remember, the total voltage change around here needs to be 0. The battery raises it up, and this guy takes all that energy. Otherwise, that would violate conservation of energy. Energy would be somehow leaving the system mysteriously without any source for it to leave. So I already know that V1 is 12 volts. Now, I don't for sure know the voltage on these two guys yet because they are going to share that 12 volts. Remember, that's the rule in series. They share the voltage. Now, based on the fact that this resistor is double this one, I could kind of visualize how this thing must break down. But let's not go there. Let's actually just figure this thing out. What I need to know in order to know the voltage for sure is what was the current that went down this branch. So in order to figure that out, I'm going to return back to this middle picture because this is a nice simple picture. Look, you have two identical branches. Therefore, these two identical branches must have equal current. And so whatever current that I got, which was the 1.6 amps, it must have broken up equally into 0.8 here and 0.8 here. So now that I know that 0.8 went this way and 0.8 went this way, I can go ahead and make the calculation. Now, I purposely made this problem so that these would be the same number. And so that does make it a little bit simpler. So let me actually go through and just manually calculate what we're looking at to just make sure that that's clear to everybody. So I'm going to calculate I1, even though I already know what it is, even though I've already figured out that half went this way, half went this way. Let's just go ahead and calculate it. So I1 would be equal to V1 divided by R1. So that is going to be 12 divided by R1, which was 15. That gives me a current of 0.80 amps. Okay. So now the voltage on these other two guys. So at this point now, I realize that if 0.8 amps went down this way, then that means of the 1.6, I would just subtract these numbers. So 1.6 left the battery, came around to the junction, 0.8 went this way, the remainder went on this way. And that remainder must have also been 0.8. As obviously because 1.6 minus 0.8 is 0.8, and obviously because the two paths have equal resistance, so no one's going to favor one path over the other. No charge is going to favor one path over the other. So at this point, I know that the current in I2 is equal to the current in I3 because they are in series with each other. That's the meaning of a series circuit. They have the same current. And that current must also be equal to 0.80 amps. And I'm using the fact that I already know what the total is to come up with that number. Okay, to come up with the 0.8. I'm just subtracting this from the total current. Okay, now with regard to the voltage, we can work out the voltage. V2 would just be equal to I2 times R2, and I2 was 0.80, R2 was 5, so that is going to give me 4, and V3 is going to be equal to I3 times R3, 0.80 times 15. And that is going to give me, oh, I'm sorry. No. Let me double check here. 0.8 times 15. Oh, I'm sorry. That's where my mistake is. I knew I made a mistake there. Sorry, times 10. I was looking at the wrong resistor. So it's this resistor right here. R3 is a 10 ohm resistor. That's a 10 ohm resistor. And I know the current through here is 0.8. So that's going to give me a voltage of 8. The reason why I knew right away that that was wrong was because I was expecting to get a voltage that was double the voltage of V2, because the resistance of R3 was twice as much as the resistance. So the same current passes through both of them. And look, the equation is I times R. So if two resistors have the same current, then whoever has the higher resistance is drawing the bigger voltage. They're using more of the energy. So that 10 ohm resistor is using more of the energy, using 8 volts of the energy, as opposed to the smaller resistor, which is only using 4. And the total of those two guys, of course, adds up to 12 volts, which is the voltage in this branch, in this path portion of the circuit. And so that's how you handle the combo circuits. They're all going to follow that same basic pattern of simplify down, find the equivalent resistance, get the current from the battery, and then it becomes an art. You need to think about, you're trying to solve the problem with the least amount of effort. I mean, you really do want to do that. You don't want to do more than you need to do. So you want to think strategically about how you can work your way legally through the diagram and really know that you're getting the voltage and the current for that section of it. All right, good luck, guys.